everybody. I'm going to go over a little bit about chirality and enantiomers and diastereomers in this video. So remember, we were thinking about a chiral molecule as being something that is not superimposable on its mirror image. Okay, that's one way to check it. You can also check to see if there's a plane of symmetry. Okay, so if there is a plane of symmetry, it is not chiral. If there's not a plane of symmetry, then it's going to be chiral. Opposite for achiral, so achiral just means without chirality, right? So that's going to be a molecule that is superimposable on its mirror image, and a plane of symmetry is going to be present. So there's really two ways that you can decide if a molecule is chiral or not. You can go through and draw the mirror image, see if you can overlap them, or even just build models of them and see if you can overlap the models. Or you can look for planes of symmetry. I prefer to look for planes of symmetry. It just kind of cuts down on how much drawing and manipulation I have to do. So if we just kind of look through these molecules that I have as examples here, let's start with the one on the left over here. This molecule, we've got CH3s both on a wedge, and then we have them evenly spaced on this 5-member ring, okay? So there is going to be a mirror plane right here. So that's our plane of symmetry. And again, we're looking for a perfect reflection, essentially, of, if you think about not being able to see this, and you just reflect that side onto the right-hand side, it should look exactly the same, and that does. So this looks exactly the same as this. So that tells us we've got a mirror plane there. So if we've got a plane of symmetry, it is going to be achiral. Okay, so then if we take a look at the next one, now I've got one wedge, one dash. Okay, so at this point, if I try to think about a plane of symmetry right here, these methyl groups are not reflecting each other in that mirror, right? They'd either have to be both on a wedge or both on a dash, but they cannot be one of each, okay? So this one, we don't have any mirror planes here. This is chiral. All right, so let's look at this molecule is acetophenone. So the acete, right, is this part where we've got the methyl and a carbonyl, and then that's the phenone, the phen part. So that is a little bit more challenging to see, because if you just think about just a straight benzene ring. So one thing that we need to keep in mind here, it's easy to let the double bonds get us confused. So sometimes when you're thinking about chirality, it's best to really think about the resonance hybrid of benzene, where we essentially have that circle of delocalized electron density. So there are about 1 million different planes of symmetry here, right? I can cut it a whole bunch of different ways and be able to still have reflection on both sides, okay? So benzene is very, very symmetric. It's even symmetric like through the middle, right? If you cut all the atoms in the plane of the paper that I have, if you cut them there, then it's going to be symmetric. And I'll just look at a model real quick of this. We're going to be switching back and forth a tiny bit here. All right, so I'm going to stop that share. Okay. All righty, so this is benzene, right? I just made a model of benzene. I've got double bond, single bond, double bond, single bond, so on and so forth. So if I'm looking here, I have planes of symmetry all through this thing, because again, we're thinking about these as not defined single or double bonds, but instead the hybrid of the two. And then the other plane of symmetry that I was talking about is the one that essentially cuts through the middle of all of these atoms here, okay? Because it's planar, we do have that plane of symmetry that is actually in the plane, okay? So if we add on the acetyl group to make it our acetophenone, okay? So if I'm looking at it like this, which is kind of how we have it drawn on the paper, this is a little bit misleading, and you go, well, I don't have a plane of symmetry here, right? Because I don't have this ketone reflecting that methyl group. So that is not really working for me. But we always need to consider bond rotations. If there is one conformation, remember conformation is just the rotation differences. If there's one conformation that has a plane of symmetry, it's going to be achiral, okay? So if we're looking at this, if there's any way that I can rotate this to get a plane of symmetry, it's going to be achiral. So if we look at it like this, I can cut in between this carbon atom, this oxygen, this carbon, this H. So if I cut all those right down the middle here, I have a plane of symmetry. So it's hard to see it here, but you can see it as soon as you do a bond rotation and you look at it like this. Okay, then I've got a plane of symmetry right there. So this is one that's a lot easier to see on a model, a little bit harder to see on the paper, but once you kind of get used to seeing them, you know that this rotation is possible off of a benzene ring and you can just cut it right in half. Okay, so let's look at that on paper now. So if that is a plane of symmetry right here, then that is achiral. Okay, so now let's look at our last option. So this diol here, again, this is a situation where since we don't have something that's initially observable in terms of a mirror plane, that's when it's really going to be beneficial to us to go ahead and build that model and do some bond rotations on it. And if you're really comfortable doing that on paper, there's nothing wrong with doing that. I'm just showing how to use the models because it's helpful, I think. Okay, so basically what we have is, I'm hoping that, I made it to my, let me change this for the camera view real quick. No, pause. Alrighty, so because you guys know the vocabulary now, basically what I'm having to do, because I'm doing this in a mirror, is I have to make it the enantiomer for myself in person so that it looks like the structure on the paper for you in the camera. So that's why I sometimes have to switch things around. So this is the structure that we have drawn on the paper, right? We have the OHs on wedges pointing towards you. So the best way to get this into something where we can see if there is a plane of symmetry is to look at the symmetry of our carbon backbone. So right now, if it's in a zigzag, that zigzag is not helpful in saying like, oh yeah, I've got a plane of symmetry right there, because the zigzag doesn't reflect itself, right? So if we just rotate one side, so then we have the chain symmetric, right? We've got this symmetric and I've got the mirror plane right here, if I'm just ignoring these. Then I can see like, okay, I've set it up so that I would have a mirror plane right here, but these two alcohols are not reflecting each other anymore, right? They are on opposite sides. So again, that's the really handy way of kind of telling if you just put it in that eclipsed conformation where you have more of a symmetric carbon chain, then you can see, oh yeah, they're on opposite sides. This is achiral, or this is chiral because there is no mirror plane. Okay, this is chiral, my gosh, alrighty. Okay, so if we're looking on paper, what we did right there, we rotated right here. We kept the left-hand side the same. So this OH is still on a wedge, which made this one on a dash. No mirror plane here. So that's going to be chiral. Okay, so that's kind of how you can think about doing it. Either build the model and the mirror image of the model overlap, or look for planes of symmetry here. All right, so let's move on to talking about enantiomers. So enantiomers, remember, we're looking at stereoisomers that are non-superimposable mirror images. Okay, that's really the important part, is that you cannot superimpose them on each other. So the best way, so there's a couple ways that we can draw out enantiomers given a molecule. So one way to do it is to just kind of imagine your mirror here and then just draw the reflection of that molecule. Okay, so anything that's closest to the mirror is going to be close to the mirror again. So Cl, the Br, and then we got a Br up here. And notice all of the wedges and dashes are all the same here. Those did not change because in the mirror they will not change. And then our double bond is over here. So one thing to really keep in mind here, if I just number these out, okay, let's say I'm just going to go 1, 2, 3, 4, 5, 6. Okay, if I put the same numbers on the same atoms, 1, 2, 3, 4, 5, and 6, look what I did with my numbering there. This one I went clockwise. This one I went counterclockwise. Okay, so that is why I was getting after you so much about making sure that when you were going from a flat drawing for a chair to another chair, that you numbered the same way each time. Because if you do not number the same way, you will inadvertently draw an enantiomer if that is a chiral molecule. And most of the stuff that I gave you were chiral molecules. So a lot of you ended up drawing enantiomers out on accident because you would switch the numbering, okay? Because you're essentially drawing the mirror image when you're doing that. So just keep that in mind. There are some instances where you want to be drawing the enantiomer and you want to do this, but you want to make sure that you have a good idea of when you want to do that and when you don't. Okay, so that's one way to draw out enantiomers, is just straight up draw the mirror image. Sometimes that can be a little bit tricky if the molecule is kind of big and complicated. So a lot of times what a really good method is here is you can also draw enantiomers by switching all the wedges and dashes. Oh goodness, let me just try that again. Okay, so everything that was wedged is going to become dash, everything that was dashed is going to become wedged. Okay, so if I take A, and instead of drawing out my mirror image, I'm just going to take A and just switch everything. So in this case, my double bond is still in the same place, but that bromine is going to be on a dash, chlorine is going to be on a wedge, other bromine is on a dash. Now if I add those numbers, I've got 1, 2, 3, 4, 5, 6. So I'm still numbering the same way, but I flipped all of the ups and downs, right? So if we look at the enantiomer of A over here, and this kind of comes into checking to see if we actually have enantiomers in the first place. If I take this, I'm going to show you the models in a second, but I'm going to show you how to do it on paper as well. If I'm trying to superimpose what I think is the enantiomer of A onto A, then I usually do a pancake flip to see if I just flip it, and we're going to say, like, we're going to take this and kind of just swivel it around that. So we're going to pick it up and then flip it over. Okay. So essentially, if we're thinking about like my thumb, when it gets flipped, it's now on the other side. So that's going to put my double bond over here. Okay. And then bromine on a dash here, chlorine on a wedge, bromine on a dash. So now we can see this flipped version has all of the opposite wedge dashes as A does. Okay, so this cannot be superimposed onto A. Okay, and this is the same as the drawing that we made down here, where we had the numbering all in the same clockwise direction, but all the wedges and dashes flipped. Okay, so let's look at what that looks like in the models. All right, so I'm going to just center myself real quick here to make sure that this is the right ones, because I'm having to do this opposite for myself. Okay, so we have these two models, right? We have the one where I've got the double bond on the left, and then double bond on the right. So once I'm here, I have them as mirror images. Okay, if I take this side, which is the one that we flipped, and I just try my best to do this, and we just flipped it like this. Okay, that's what we did. So if you're having trouble flipping stuff on paper, just know that when you do this, we've got the bromines, which are in blue. The bromines are on wedges sticking out at you right now. When we flip it, they switch sides, and now they're on dashes going away from you, okay? So if we try to line this up, we are getting exact opposite sides for the bromines and the chlorine, okay? Where our alkenes are lining up. The other way that you can look at this is if we just try to line it up without flipping it. So this actually looks pretty decent, right? Until you look at the fact of what my hands are hiding, where my alkenes, I've got one alkene here and one alkene here. So the alkenes are now not lining up, right? Because if you think about what I've done here, is the only reason that I have a chiral molecule here is actually because of the double bonds messing up this potential plane of symmetry right here, right? If I did not have this, I could just cut this right here, plane of symmetry, it would be achiral. But since I have this breaking my symmetry, then it's going to be one of the things that's messing up this overlap, okay? All right, so let's go ahead and keep getting this drawn out. All right, so we've talked about some flips, talked about the numbering here. So these are enantiomers, okay? This is another enantiomer of A. I'm just going to make sure that I have it all labeled here. And this is an enantiomer of A. Okay, so all of these drawings are identical. Okay, this is the only one that's kind of the odd man out here. So that's how we want to be thinking about enantiomers. Draw out mirror images, make models, try to overlap them, and see how that goes. Alrighty, so diastereomers, we're looking at stereoisomers that are not mirror images of each other here. So my best advice for diastereomers is swap how do I want to say that? 1 to 1 less than total. And I'm going to explain that. Of the stereocenters. Okay, so what I mean by that. So swapping 1, and in terms of stereocenters, I'm going to talk about that in another video a little bit more, but stereocenters are just carbons that have 4 different substituents on them. So for example, this carbon has an H, a bromine, a carbon with a chlorine on it, and a CH2. That's 4 different things. So these 3 carbons are all stereocenters. So what I can switch here in order to make diastereomers is I can switch 1 or up to like 1 less than the total, okay? If I switch all of them, then I'm drawing an enantiomer. So I have to keep it kind of 1 fewer than the total number of stereocenters, okay? So that means that's the one thing that we should think about here is that any chiral compound with just 1 stereocenter can't have any diastereomers, okay? So 1 stereocenter can only have an enantiomer, not a diastereomer. Okay, so diastereomers are really something for 2 stereocenters or more, okay? 1 stereocenter, we're only going to be able to have the enantiomer, right? Because if we flip all of them, we're in enantiomers, okay? All right, So let's look at the A example that we have again. So we can swap up to 2 stereocenters here. Okay, I've got 3. If I switch all of them, I'm doing enantiomers, which we already did. So if I'm switching 1 or 2, then I'm going to get diastereomers. Okay. That's a diastereomer. Okay. I just switched the chlorine atom from a dash to a wedge, right? These, no matter how you try to line it up, are not going to be mirror images anymore. But they're also stereoisomers, so they're different in 3D space. So let's look at changing 2. Okay, that's going to be a diastereomer. And it does not matter which ones. Right, all of these are diastereomers. So let's look at the models and see what that kind of looks like in terms of the mirror image part. So these are my original mirror images. So I'm going to keep this one the same. So I'm not going to change this guy. And instead, I'm just going to take this chlorine and put it on a wedge. Okay, what that's done is now they're not even mirror images of each other, right? I've got my chlorines in totally different orientations here. So some of it still looks like a mirror image, but these two are not anymore, okay? So they're not mirror images. That's actually a better way to see that they're not mirror images. Not mirror images, but still different orientations in space, okay? So that's what we're really looking at. So for diastereomers, just switch. You can just get away with switching 1 and then you'll be fine. So definitely this is going to take some practice, and we're going to make sure that we kind of know the difference between what's an enantiomer, what's a diastereomer, what's the same molecule, and make sure that we get comfortable with that kind of like flipping of molecules, rotating of bonds, and all that stuff. And the models will be your best friend. So let me know if you have any questions, and I'll talk to y'all later.